for our the flip flops.
You had a
When we're
question about enable for your flip-flops, okay.
Yes, and then also asynchronous reset, which is what we worked on before. If I remember correctly, enable is for the flip flop, right? While the asynchronous reset is for the latches.
Say that one more time.
When we're working out that problem to where we had to make a new modified D flip flop, we had to implement the asynchronous reset, which we've already done. While the enable one, I couldn't remember properly, but if I remember, that will be on the flip flop itself, right, rather than the latch.
So for the enable signal, is
Hmm.
well, you can think of it like this. What's the purpose of the enable signal?
Um, well, for what they had in the context of the test, it was, I believe, if it was one, it would be just taken D input, and then if it's zero, then it would just be Q previous, if I remember.
Yeah, so one description of it is as follows. Enable, if enable's on, then it behaves like a regular flip-flop. If enable's off, it doesn't read in on every clock edge, it just retains its current value. That's what enable does.
I see.
So you can think of enable being off, meaning you're disabling the register from reading in the value. So that's the purpose of the enable signal. And knowing its purpose, now we can ask ourselves, okay, should I have to introduce it into the circuit in an asynchronous manner, like the asynchronous reset, or in a synchronous manner? What do you think?
Um, I believe it should be asynchronous.
I think you can do it just as a synchronous signal. You don't actually have to open up the internals of the flip flop. You can do
Oh,
it
I
as an
see.
external thing. Um, the reason why is because, remember, like we said, enable affects whether or not you're reading in D at the clock edge, but it's at the clock edge, so it's synchronized, not asynchronous like reset, since it's at the clock edge that you're reading in from D. And so what that means is you don't have to open up the flip flop. You can do it as external logic outside the flip flop leading into it.
I see.
So if you want, like, I can draw out what you would need to put for an enable, if you'd like. I can do that.
Yes, please.
Yeah, sure. So grab my new expo markers. Okay. So what I have here is kind of like a black box diagram. Cool. Can you see the circuit on the board?
Yes.
Yeah, so what I have here is a black box diagram for a register that's enableable. And so all I'm going to do is I'm going to try and write a truth table to describe the operation it's enabled. Okay, so if enable is on versus being off, that's going to affect what we're trying to read into the register. If enable is off, then that means that DN is going to be whatever Q is. So it's going to be the output of the register. Whereas if enable's on, it's going to be whatever D was originally going to be. So the original wire leading into the register. And so what we can do here is we can write out the equation for this output. So DN is going to be on if enable is off and Q is on. Or in the case where enable is on and D is on. So that's the logic that we're going to have at the front of this register. And so it's going to look like this. So we're going to have an OR gate, which has two things coming out of it, and each of those two is an AND. So for this first AND gate, I'm going to have enable bar ANDed with Q. And then for that second AND gate, I have enable with D. And so let's go ahead and run through this logic one more time to verify that our truth table actually matches the way we want this to work. So first, I'm going to set enable to 1, because remember the way we want this to behave is if enable is on, it behaves like a regular D flip-flop. So if enable is on, then this input of this AND gate is 1, and this input of this AND gate is 0. And so what that means is that the output of this AND gate is 0, and the output of this AND gate is whatever D is. If D is 1, this is going to be 1. If D is 0, this is going to be 0. And so then what you're doing is you're doing D ORed with 0, and so that means that D in is just D. So are you cool with that analysis there?
Yes.
Okay. So when enable is on, it behaves like a normal flip-flop. And now we can talk about when enable is off. So when enable is off, remember that we want it to just read in the value of Q. So let's see if that happens. So enable is off. That means that this AND gate has a 0 at one of the inputs, so its output is going to be 0. And this AND gate has a 1 at one of its inputs, so its output is going to be whatever's on this wire, which is Q. And similar to before, we have Q or 0, which is just Q. So it retains its previous state. And so this operation of this truth table, this equation derivation, we've just verified that it actually works the way we want. And so that's the way you would design an enableable flip-flop with logic at the front. There you go. Okay, so any questions about that?
No questions. So this will just be for one register, right? Or this will be a flip-flop?
Well, a register and a flip-flop are kind of interchangeable.
Mm-hmm.
They mean the same thing.
Okay.
Register, you typically call it a register when you... Well, typically they're called registers when you use them for... what's it called? Like an assembly code, when you have like 32-bit registers. Typically, if they're in groups, multi-bit registers, they're called registers, where if it's a single, you can refer to them as flip-flops, but I use them interchangeably.
Oh, I see.
So yeah, that's a register. It's also a flip-flop. Doesn't matter what you call it. Okay. Did you have any other questions for me?
To combine that with the asynchronous reset, we would just need to take in that output of the OR gate with and then do what we did with the asynchronous reset from before, right?
Yeah, exactly. Yep.
Oh, okay. Thank you.
Yeah. By the way, how was the exam? Did you feel like it was well, what did you think about the exam?
I made a big mistake in that I came in late, really late.
Yep, that would do it.
Yeah.
How much? How late did you come in to class?
Came in at 10:44.
10:44.
Class started at 10 o'clock.
Were you the one who handed the exam into Dr. Harris in her office?
Yes, I was.
Okay. Yeah, I was there because we were in class. That makes sense.
What class was that?
It was 795, which is high-speed PCB design.
Oh, okay.
That makes sense. Okay, so that's why you turned in your exam then. I see.
Yeah, that late, yeah.
Okay. Did you manage to write something for every question at least?
For 2 questions, no.
For 2 questions? What were the questions?
Yeah. If I remember correctly, it was the second finite state machine that was supposed to detect fours, I believe.
It was supposed
to detect 4s, 8s, 12s, like groups of 4s, I believe.
Oh, I see.
That one, yes. And then the other one was the system Verilog code, the very last one, where it was...
it was like an FSM, right?
Yeah, an FSM. And so, yeah, those 2 I didn't get to it, but the other ones I did.
Okay. Well, if there are any particular homework questions you want, or exam questions you want to talk about, we can go over them, like those ones that you didn't finish, or any of the other ones. I don't mind going over those.
Okay. Yeah, so then can we try the one that detects like the groups of fours?
Yeah, sure. So what's the input? So it's a you are you receiving a single wire that's sending series bits or
Yes.
okay, so it's a single series bit. And how long is your number in bits? Is it like a 2-bit number? Is it a 20-bit number?
I can't remember from the top of my head. But it was essentially, I think it might have been continuous because it was saying, one fours, one eights, one twelves, etc. So I thought that that meant like, I don't think that it should be because then that kind of defeats the whole purpose of finite, right?
Could you do me a favor and uh, yeah, could you do me a favor and type an example sequence that you'd be provided in the chat just so I can kind of get an idea of what like inputs we're
Okay.
looking at?
Hmm. I think it was working off of the previous FSM problem that we had, like detecting 00101, and then um and then
Oh, by the way, you don't have to type it in the general chat. In the voice channel, there's a little open chat button, so it's specifically
oh,
for
okay,
our voice channel, just so
I
that
see, I see.
the others don't have to deal with it being, you know, in the general chat.
Okay, I believe this was the original for the FSM.
Okay,
Somewhere similar to that.
and what was it supposed to detect?
It was um for the original question.
So, like, if you put that as the input, what would you expect the FSM to output?
It was supposed to output like oh, sorry, what do you mean?
So your input that you just sent your FSM, you sent 101100. But
Hmm.
what's your FSM supposed to be out? What's the output signal of the FSM supposed to even say?
Oh, it was just one bit.
So it's a 1-bit output, and then what does it indicate? Because you said it detects fours. When you say detect fours, I'm trying to think of how to interpret that.
Hmm.
Does that mean like the number of ones that are in the sequence? So like you're counting how many ones you've seen, and if it's a multiple of 4, then you output true.
I believe so, yeah.
Okay, that makes sense. Okay. Because originally, before that, I was thinking that you meant you received a number and you were checking if it was a multiple of 4.
Oh, okay.
But that's not what, according to this, that's not what's happening. You're receiving a binary sequence 010101, and you're
Hmm.
counting how many ones there are and just checking if if the number of ones is a multiple of 4.
Yes.
Okay. So here's the basic idea. We're going to be talking a little bit about modular arithmetic, not like in a very detailed sense, but just like as a general thing. If you're starting at a number, say 0, that's a multiple of 4. And then when you go up from there, you go up to a multiple of 4 plus 1, which is the number 1. And then if you keep going up, you go to a multiple of 4 plus 2 and a multiple of 4 plus 3. But then when you go up by 4, that's a multiple of 4 plus 4, which is another multiple of 4. So you kind of have this cycle where you're multiple of 4, 4 plus 1, 4 plus 2, 4 plus 3, and then back to a multiple of 4. So in my head, I'm thinking this is going to be a 4-state FSM, because if you're thinking about multiple, whether or not something's a multiple of 4, there are only 4 options. It's a multiple of 4, 4 plus 1, 4 plus 2, or 4 plus 3. So that's kind of the train of thought I'm going with here for this FSM. Does that seem reasonable to you?
Oh, yeah, that makes sense.
So if I was to actually do it, it would be something like this. So I haven't finished drawing all the transitions. I haven't like labeled them or anything, but this is kind of the general idea I'm thinking. So a multiple for 4n, a multiple for plus 1, multiple for plus 2, multiple for plus 3, and then back to a multiple of 4. And what should I write for these transitions? When do you take a transition?
When do we take a transition?
Yeah, like what'll cause me to go from a multiple of 4 to a multiple of 4 plus 1? What must have happened with my input?
1, right?
Exactly, yeah. We received another 1, so we kind of increment. We go to the next one. And what would happen if we didn't receive a 1? Where should I transition to?
It just stays the same, right? For
Exactly,
each state.
yeah. It's like not adding anything to it. If you're at 4n and then you add 0 to it, you're still at 4n, so you stay in your same state. And so I imagine, assuming that we got the idea of the problem right, I'm going to assume that this is what we actually want to do. This is the FSM for it, so it should be 4 states, one for each transition. And were you asked to do this as a more or a melee? Because I've done it as a more FSM up on the board.
I believe the previous question was a melee, and I don't remember it stating whether it was a more or a melee. But I'm thinking if the previous one was a melee, then this one would probably be a melee as well.
If the previous one was melee, then this one's probably more, so you have one of each. At least that's my guess.
Oh, okay.
I don't actually know. I'd have to look at them. But I'll just assume it was more. This would be the more FSM for that problem.
Yes.
Do you have any questions in regard to the way I came up with this or anything like that?
Oh, no, that makes sense.
Okay. So are you comfortable, now that we have this diagram, would you be comfortable then going to the tables and then the equations and then the schematic?
Yes.
Okay, cool. Did you have like any other questions about just this problem in general?
I guess maybe it's just on like modular arithmetic. So it's all just about the modulus, right?
Yep. Yeah. It's not like outright stated in the problem description, but that's the way I'm thinking about it. Yeah.
Mm-hmm.
Yep. That's right.
Okay.
And you could do a similar FSM for, modulus 2 or modulus 3, modulus 5. You'd have as many states as you do whatever you're modding by.
Mm-hmm. Okay, thank you.
Yep. Okay, cool. So we've talked about this problem. Were there any other problems you wanted to talk about?
Yeah. So for the timing one, I believed we were given 3 buffers for our skew, and then it had between 5 to 25 picoseconds.
So the delay of the skew was between 5 and 25 picoseconds? So like
Yes.
some unknown number between those? Okay, cool.
Yes.
Okay.
Yeah.
And what else were you? So you were told a range of the skew, and what were you asked to do?
I believe we were to find the maximum frequency, I believe.
Okay. So the maximum operating frequency. So we covered something similar to that last time. So were you given a direction of the skew or no?
Yes, it was left bias.
So left bias, so it was point to the left?
Yes.
Okay, cool. Just so you know, left biased and right biased, as far as I'm aware, those aren't like, that's not the actual terminology. I just use that for my own, like, just in my head. I think of it as left biased, right biased.
Oh, okay.
I think the proper terminology would be, if it's left biased, you would say clock 2 leads, because it receives the clock first, and clock 1 lags, register 2 leads and register 1 lags. And if it was right biased, that means register 1 would receive it first, so register 1 leads and register 2 lags. That's more, that's terminology you would probably actually hear. So you might not hear other people say left biased and right biased like I do, just so you know. Okay, so let me go and draw that out. Okay, so with this left biased skew, which is to say that register 2 leads register 1, can you tell me which where I'm going to add skew to my equation?
Now that you said it, it does make sense. Why we add skew. You would add it to to TC and T hold, right?
So, TC. So I can draw the diagram out, and we'll take a look at which one it is going to be. So and remember that 2 leads 1. So 2 comes earlier in time. And we're going to figure out, okay, where do I add my skew? Because on the diagram, this is my skew right here, that distance between those 2 clock edges. So what we're going to say is, analyzing for this equation, we're going to have some starting value. So the time to be read out of the register, TPCQ. We're going to have some propagation delay through all of our logic. And then we have some setup time. Now, let's pretend for a moment there was no skew, and they both had the same clock as 1. Would this work?
Sorry, what do you mean by work?
So when I mean work, I mean that your operating frequency is slow enough so that your logic has time to propagate through and get read into the register.
And that's if there's no clock skew, right?
Yeah, so let's pretend the second clock wasn't there. Let's pretend both registers have clock 1. Looking at the timing, do you think that this would work? Do you think that the registers would be able to read in the values on time?
Yes.
I think not. So here's why. This is the delay to get read out of the register. This is the delay to go through the combination logic. And this is how long you have to wait at the entrance of the second register, and you have to be steady. But here's the thing. We have, assuming there's no skew, a clock edge here in the middle of T setup. So at that point in time, my signal could still be trying to get steady by that point. We have no idea. Only after this time here are we guaranteed that the signal is steady. So since the clock edge is back here, we actually don't have a circuit that's running reliably. We'd have to extend the period so that all of this time fits within. So for this equation, if you're looking at your timing diagram and it goes further than one full period, it doesn't work. The frequency is too short, or the frequency is too quick, and so you need to elongate the period, make a longer period. Okay, so any questions with what I just said?
No questions.
Okay, so with that in mind, now we can think about what happens with the skew. So when register 1 reads out a value, and now what we're going to look at is when register 2 is expecting an incoming value. So register 2, remember register 2 leads. So this was its first clock edge, and this is its second. It's expecting to be able to read in here. Now, is this worse than before or better than before?
Worse than before?
Yeah, we have to extend the period to be even longer because we went further to the left. So this would be the worst case scenario. So this skew made our circuit work worse. So that's the worst case scenario for TC. And so in my head, I'm thinking, okay, well, this skew made it worse for TC. So where should I add it? To the right-hand side or to the left-hand side? And why does that make it worse?
We add it to the right-hand side because that increases the period, right?
Exactly. You add it to the right-hand side because that makes the period longer. Very good. In general, if it's left biased, you add to the right-hand side of the equation. If it's right biased, you add to the left-hand side of the equation if you want like a quick way to remember it. But this diagram is how you could derive it on the spot. And that applies for both the TC and for the T-hold. So when it's left skewed, you still add to the right-hand side in both equations. If it's right skewed, you add to the left-hand side. Sorry, I think I might have said that poorly. When it's left skewed, you add to the right side, and when it's right skewed, you add to the left-hand side. It's always the opposite. Here, though, for our hold time constraint, this is the best possible case. And the reason why is because on the left-hand side, the hold time, if we ignored the skew, T-hold has to be less than these two terms together. So pretend it was, say, 20 picoseconds. And if the hold time was less than 20 to begin with, it's definitely still going to be less than 20 if we add skew. Because no matter what this number is, if it's less than 20, say it's 17, 20 plus whatever is definitely going to be less than 17 because this is some positive value. And sometimes, even if this hold was greater than 20, say it was 22, if we add 3 picoseconds of skew, then 22 is now less than 23, and that actually benefited us. Before the skew, our circuit couldn't run because the hold time constraint wasn't met. But after the skew, now that we've added the skew, our circuit can actually run reliably. So this is the best case scenario for the hold time, but the worst case scenario for the clock time, or for the setup time equation. Okay, so with that in mind, the next steps of what you'd have to do would be first check the hold time equation. So you'd have to find the shortest delay to be read out of the register plus the shortest path through the combinational logic plus, and then we need to think of the worst possible case for skew. So the lowest that the skew is going to go is to 5. So we'd have 5 here and then whatever those sum to, and we'd have to check that the hold is less than that. So any questions about checking that part of the equation?
So it was for T skew, as you said, for T that will be 5 because it's for T hold, and then it'll be 25 because it's for TC.
Not necessarily. So we're just considering the worst possible case. So,
okay.
So it's harder to meet this requirement if skew is small. If skew is really, really big, then we can meet this requirement for this equation really easily, right?
Mm-hmm.
So by choosing the smaller skew, that's the worst case scenario. Ideally, this skew would be 0, or sorry, in the worst possible case, this skew would be 0, and that would make it so that this T-hold has to be less than this value. But the bigger we make the skew, the easier it is to meet the constraint. So we pick the smallest value because that's the worst case. So that's why I picked 5 there.
Oh, okay.
And then we do pick 25 for TC because in the worst case scenario, we say, okay, there's 25 picoseconds of skew because that makes our period longer. That's the worst case. So yeah, we'd use 5 picoseconds for this guy and 25 for that guy. Okay, so like I said, you'd figure out this value, find if your hold time constraint is met. If it isn't met, if it's not met, then you say circuit doesn't operate reliably. And if it is met, then you're going to calculate what the clock time is. So you would find the longest delay through the clock to get from clock to the output of the register. So that's given to you. and then you'd find the longest path through the combinational logic, whatever that is, and you would have the value given to you of the setup time of your register, and then you'd add 25 picoseconds to that, and that would be your clock time. So say it was 250 picoseconds, and then you would finally take that value and take the reciprocal of it to get the frequency. It'd be 1 over 250 picoseconds, which is 4 gigahertz, and that would be how to find the clock time, or rather the frequency.
Mm-hmm.
Okay, so
If I remember, sorry.
Go for it.
Oh, sorry. If I remember, it was like the cycle time was actually like one. It was like 1,000 picoseconds.
Yeah, there's probably a lot of circuitry in here. Yeah.
Yeah. Or no, they just gave us they actually just gave us the contamination delay and the propagation delay.
Oh, there you go.
Yeah.
Yeah. So whatever those values were, you add 25 here, add 5 there, and then you just do those calculations.
And for to get the frequency, we just have to divide that 1 over your period times 10 to the power of 12, right?
Yeah.
Negative 12.
Yep, that's right.
Okay.
Yeah, that's about it. That's about it for this question. Besides, like actually having the numbers and plugging them in.
Yeah.
Any other questions about this?
Maybe just on like just a simple question about like significant figures, I guess, because we were asked to convert from gigahertz to megahertz, in which I just just divided by 1,000 because, and would that just work? Like, or how many? I completely forgot about significant figures.
Oh, I think 3 is generally good, but you could also theoretically just on future tests ask her what she wants.
Oh, okay.
Or possibly at the top of the page say, I'm going to assume you want X sig figs, and then do that many, and she'll be fine with it.
I see.
I'm sure as long as you didn't do like 1 sig fig, I think she's fine.
Mm-hmm.
All right. You got any other questions for me?
I don't think so. I think we went through a lot of the questions I had when I was taking the test.
Okay, good.
Thank you very much.
You're very welcome. Okay. Are you alright if I erase the board, by the way?
Oh, yes.
Cool.
No one else came?
No, there's no one else. I mean, I expected no one to come, if I'm being honest, because who comes to office hours on the day of the exam?
That's fair.
Doesn't really
That's
make
true.
sense. But, I imagine they're just taking a break because exams can be pretty draining.
Yeah.
Okay, cool.
Well, since those are really all my questions, I guess I'm done. Yeah. Thank you very much.
Yeah. You have a good rest of your day.
You as well. Thank you.
Go ahead and pause the recording.